Hey guys, what's the crack? So in this video, we're going to go over what the main types of waves are. Like, how do we really understand what a wave is? And then we're going to look at, can we figure out what the path difference is here between these two waves to figure out what the phase difference is? And then we're going to look at what is polarized light. And we're also going to see, can we figure out what's going to happen to point P and point Q over time? So what's going to happen to point P and point Q over time? So to start with, we know there's two main types of waves. We have both longitudinal and we have transverse waves. Believe it or not, I have marked past paper questions from different schools before, and they didn't know what a longitudinal and a transverse wave was, and that can come up in your exam, so just make sure you lock down those definitions. So remember, a longitudinal wave is things like sound waves, okay? So longitudinal waves, we know that the vibrations, or you can say the word oscillations, that vibrations are parallel to the direction of energy transfer, right? So we're making it very clear that we know that it's energy that gets transferred along. It's not the particles that move along, right? So for example, when I'm speaking right now and my vocal cords are vibrating, what's happening is it's not that an air particle beside my vocal cord is shooting out towards the microphone. That air particle is going to vibrate, it's going to make the next particle vibrate, the next particle vibrate, and so forth until that energy gets transferred along to the microphone. So it's the energy that gets transferred. Whereas transverse waves, you write the exact same sentence, the vibrations are perpendicular to the direction of energy transfer. For example, if we have a light ray that is coming down, because we know all EM waves are transverse waves, so electromagnetic waves, that's like your radio waves, your infrared waves, your X-rays, your gamma, your visible. So let's say we have a ray of light coming downwards, all the particles we know are going to vibrate or oscillate perpendicular to that direction of energy transfer, right? It's not the particles are moving down, they're just vibrating or oscillating in that direction. Okay, so again, all transverse waves are all your EM waves and also water waves. Okay, other thing you want to know about longitudinal waves is because they're called sound waves, we can call them waves that we have areas of compression and rarefaction. Okay, so compression and rarefaction. So what that means is, let's say a sound wave is traveling along, an area of compression is when all the particles are much closer together. An area of rarefaction is where they're further apart. Area of compression, where it's much closer together. And then area of rarefaction, again, when the particles are much further apart from each other. Area of compression, when the waves are really close together, and then area of refraction, where the particles are really far apart from each other. Okay, so that's what our longitudinal waves are like. Okay, the key thing is, and that's where it gets harder from your GCSEs, is that from GCSEs, you always see these pictures of waves, and everyone always thinks the wave is showing us like what's the particles doing. So for some reason, people always think that the particle starts here and the particle takes this direction, right? But that's not what's happening, okay? What it's showing us is that's a snapshot in time. So remember, let's say this is our transverse wave and the wave is traveling towards the right. Okay, so what's going to happen is every particle, let's say a particle is here, that particle is going to vibrate or oscillate perpendicular to the direction of energy transfer. If there's a particle here, it's going to vibrate or oscillate perpendicular to the direction of energy transfer. And we call these waves, they're progressive waves. Okay, they're progressive waves because what's happening is energy is traveling along free space. Okay, so what's happening is our energy is moving towards the right. So our energy here is moving towards the right. And what's happening is every particle on this transverse wave, on this progressive wave, has the exact same amplitude. So remember what amplitude is that maximum displacement from its equilibrium position. So the equilibrium position is that middle line. The maximum displacement from the equilibrium position, that's what we call its amplitude. So it can go maximum position in the negative direction and in the positive direction. So that's what its amplitude is. Just a reminder there that the amplitude is the maximum displacement from the equilibrium. Okay, so what we're seeing here is, if I just change my color to show where the particle is at a certain time, this particle that we had the drawn with the black dot here, that particle is currently up here at its maximum amplitude. Okay, the particle here with the other dot that I drew here, it's currently at this point of its vibration. So what we're saying is every particle right now, that's where they currently are, right? That's where we took a snapshot of them. Because remember what the particles can all do is they can all vibrate for that maximum amplitude, for that maximum displacement. We took a snapshot in time to show us where they are right now, right? So remember this red particle here, if I look at this one, it's not going to move this direction. What it's going to do, it's going to move down or it's going to move up over time, okay, because it can only move upwards and downwards. So again, you have to imagine that the particles are all somewhere along. So again, if we saw this, that's where my particles are all at this time, and then what we do is we just draw the wave by joining them all together, right? It's not saying the particles are moving in this direction, it's not saying the particles move in this direction, because we know the particles can only vibrate or oscillate perpendicular to the direction of energy transfer. So it's really important that you understand that, because you might see an exam question that says, what's going to happen to point P? So let's say this question says, what happens to point P? Okay, and it might say over one full cycle. Okay, so what I'm going to do is, again, I know my wave is traveling towards the right, so what you want to do is you want to sketch the wave later in time. So I'm going to just sketch a little wave right beside it, just slightly later in time. So hopefully you can see my green dotted line is this going to be this wave slightly later in time, because my wave is moved over towards the right. So it's my wave slightly later in time. So if I look at point P was here as my amplitude, so clearly that point P has moved down, right? Because the green dotted line shows me the particles are over time. So point P is going to move down. We know it's going to move down to the equilibrium. Then it's going to go down to its amplitude or its minimum displacement. Then what's going to happen is it's going to go back up to the equilibrium. And then it's going to go up to that maximum amplitude again, or to that maximum displacement. So we're saying particle P is going to go the whole way down to its equilibrium, it's going to go the whole way down to the maximum amplitude, going to go back up to its equilibrium and back up to where it started. That's one full cycle, okay? So let's just say to practice again, the question said, what's going to happen to particle Q? So we change the color to purple. So again, my green line, so let's say we're looking at particle Q now. My green line is later in time. So if I look at particle Q, it's had it gone up over time. So Q will move up first. That's what it does first. It's going to move up. It's going to move up all the way to its maximum amplitude. It's going to go back down to its equilibrium, back down to its amplitude in another direction, and then back to the equilibrium where it started from. That's a full cycle. So Q will move up first in time. Okay, so we just draw a dotted line showing a wave later in time to see what the particle is going to do. Okay, the next thing you need to know about is we need to know about phase difference. Okay, so you might have heard before that you need to learn this equation, right? It's not given to you in your data sheet. Okay, so you need to know that phase difference, what it is it equals our path difference divided by the wavelength multiplied by 2 pi. Okay, so divided by the wavelength multiplied by 2 pi. So let's say, for example, I have two slits here, right? So I've got waves coming out of slit 1, I've got waves coming out of slit 2. And I want to see at point P what's happening. Okay, so what I want to do, I want to know what the phase difference is at point P. So to find the phase difference, I have to see the path difference. So what that means, it just means the difference that they have traveled in path, right? The difference in distance. So from slit 1, it traveled 7.8 meters. And from slit 2, it traveled 9.4 meters. So we take those two numbers away from each other, the path difference is going to be 1.6 meters. Let's say, I should have told you before, but let's say the wavelength is 0.8 meters. So what I do is I do my path difference. So they traveled a total distance. So slit 2 clearly traveled, that wave from slit 2 traveled 1.6 meters further than that wave from slit 1 as the path difference divided by the wavelength, which is 0.8, multiplied by 2 pi. So when you do that in your calculator, when you do 0.6 divided by 0.8 multiplied by 2 pi, you're going to end up with 4 times pi radians. Right, so that's going to be my phase difference, 4 pi radians. Okay, so next thing I want to do then, when I want to learn about waves, is want to learn what polarized light is. Okay, so polarized light. So we know that light from light bulbs, light from the sun, what it means is unpolarized light. Okay, so we're looking at our transverse waves. Okay, so transverse waves. So we know transverse waves, remember what it means is that oscillations vibrate perpendicular to the direction of energy transfer. So what's happening here, we can see, let's say the energy is being transferred towards my eye, right? That's where my eye is, the observer. So what's happening is all of the particles are going to vibrate in every plane that is perpendicular to that direction of energy transfer. Okay, so again, if they go in this direction, my particles can vibrate this way, perpendicular direction of energy transfer. My particles can vibrate this way, perpendicular to energy transfer. They're going to vibrate in every plane that is perpendicular to that direction of energy transfer. So what happens here? So again, this is my unpolarized light. We have this thing called a polarizer or a Polaroid. So let's say it's a Polaroid. or here, again, it's polarized light, but let's say it's Polaroid, or a polarizer. Okay, so again, what I have is my polarizer or Polaroid. What you can basically think of that is you're basically kind of imagine it like it's a solid sheet, and in the middle of the sheet there's a hole. Okay, it's kind of what you want to imagine it. So it's kind of like a slit again. So middle of that sheet there's a hole, and the hole is going to only let through oscillations or vibrations that are in that same plane. Okay, so again, let's say we look here, all the waves are vibrating in all directions perpendicular in a transfer. But because this is in the plane that is in the, let's say it's orientated in this direction, the way the axis is, it's only going to let through the waves that are traveling that same direction. So you see here, only the waves traveling through in that same direction get through. Only the ones that are vibrating in that vertical plane. If I have another polarizer here, so there's my second polarizer, if it's also at this angle, what's happening is, again, we're going to allow all the waves that are vibrating in that direction through. So I do see light coming through me. So even though I've got a polarizer, two polarizers, I still see light come towards me. You've probably heard of polarized glasses or polarized sunglasses. What that does is, again, it reduces the glare because it cuts out or it gets rid of some of those planes of oscillation. So then less light is coming through. So you see here, we've got loads of light, but here when we have our polarized light, what that means is we're only getting vibrations or oscillations on one plane. So again, polarized light is when we have vibrations or oscillations in one plane, right? We don't have all the planes anymore, okay? So now let's imagine the second one, right? The second polarizer. What if I orientated it through 90 degrees? So what if I put it in this direction? So remember, there's my plane that's going to let the waves through, my slit through it. Clearly, if I only have waves vibrating on one plane in this vertical plane, if I was to put my polarizer horizontal, none of the waves are vibrating that horizontal direction. So there's going to be no waves get through, so I would see nothing. Okay, so again, what I'm saying is if we have one polarizer in this direction orientated at 90 degrees to a second polarizer, we're never going to get any light through because the first polarizer is only going to get light through in the parallel direction, and the second polarizer is not going to get any light through because none of that vertical has any components in the horizontal direction. Okay, so we know we're vertical and horizontal independent. So let me show you another example. So let's say we have our unpolarized light that's vibrating in all oscillations, all planes to direction of 90 degrees, that energy transfer. Let's say we put our first polarizer in the horizontal direction. Again, what we're going to do is we're only going to let light through that is vibrating in that horizontal direction. So we're only getting light through that's vibrating in that horizontal direction. If I was to put a second polarizer here, again, in that same orientation, again, I would get light through, right? Because I've still got horizontal plane, so I am going to see some light coming through. But if I took that second polarizer and I put it at 90 degrees to the first polarizer, or the first Polaroid, so there's my second polarizer, if we put it at 90 degrees, so now we're only going to get light passing through that's vibrating in this plane. Clearly, because the light's already been polarized and I'm only getting that horizontal through, there's no components in the vertical direction, so no light will get through, so I'll see nothing. So a common question might be, if you have a diagram and you want to see how does the intensity of light vary when we change this second polarizer. So let's say we start off with our blue picture, right? So again, we're going to start with our blue picture where we got both of the polarizers in the same direction, the same orientation. So clearly we know that we are going to get light through. So at 0 degrees, we're going to get maximum light through. If I rotate the second polarizer about 90 degrees, so let's say we rotate the second polarizer to 90 degrees, what we said is because there's going to be no components, there's no horizontal components here, so my intensity of light is going to drop down to 0. Let's say I rotate it through 180 degrees. So if I rotate this through 180 degrees, so another 90 degrees, it's just basically upside down. But it's upside down, it's still going to be letting through those vertical components. So again, my intensity of light is going to go back up to maximum. Let's say I rotate it through 270 degrees. So again, I rotate it for another 90 degrees to get 270 degrees. It's just flipped, but it's still in the horizontal plane. I'm going to get no light through because again, we only have the vertical component. So what's going to happen is my light is going to drop back down to 0. Then if I swip it back 360 degrees, so rotate it another time again, we end up back where we started, in that same direction. So again, I'm going to get my light is going to go back up to a maximum. So we can see how the light intensity varies. So again, if I've got unpolarized light and I put one Polaroid, I'm going to polarize the light and let light through that only vibrates in one plane. If I put a second polarizer in the same orientation, I do see things because it's the same orientation. But if I put it at 90 degrees or right angles to the first Polaroid, I will see nothing because none of that light will come through. So hopefully you find this video helpful, and then remember to check out the rest of the videos on this topic when we start to go into what refraction is.